All right. So what I want to discuss today is sort of a direction that things are going in dark matter research. So we've spent a lot of time talking about thermal histories and WIMPs and building up our cosmological intuition. And so where we kind of ended up on Tuesday is this idea that there's the WIMP, which was a tremendously influential idea, the WIMP miracle that suggested that we should, have motivations for weak scale dark matter candidates. But the field is moving in a different direction at the moment, and that's kind of where I want to go today. And the reason for it is that, well, on the one hand, a lot of stuff has been done with WIMPs, and there's just only so much you're going to do there. The second reason is that the promise of WIMPs was always that we would go and we would build these direct detection experiments and we would discover dark matter, or we'd build the LHC and we'd find weak scale particles there, and neither of those things happened. So at the very least, the intuition, the ideas that people had of what was going to happen weren't realized. That doesn't mean WIMPs are wrong. There are lots of WIMP models out there that are still very good and viable. But at the very least, a lot of parameter space has been explored, and so people are looking to alternatives. And thirdly, I think that people are trying to be a bit more systematic about their approach to thinking about dark matter. Rather than simply taking top-down models or trying to start within supersymmetry or some specific beyond the standard model, people are simply starting with effective field theories and trying to build out what kinds of dark matter models might make sense. So the kind of stuff I want to talk about today is very, very much ongoing. It's also very, very much a young person's game. I'm like one of the really, really old people now doing this stuff, and I'm not that old. So let me describe to you sort of the basic framework that people are thinking about these days. Okay, so the basic idea is that you have the standard model over here, and that you have a dark sector. Okay, and oftentimes for WIMP models and similar models, like the idea was very simple, that you simply add one new particle, or you take the standard model and you extend it, and then in that thing you find a neutral particle, and that the sort of dynamics of it are basically uninteresting. There isn't anything going on there. The idea of this setup is that you have the standard model with all of its particles and Higgses and strong interactions, and then you have a dark sector, which could be complicated at any various degrees. It could be simple, it could be complicated, but it's there. That's the idea. And something in it is the dark matter. And something should connect us to the dark sector. Why should you be connected to the dark sector? Well, in principle, there's no reason why you have to be connected to the dark sector. But there's this old joke, you've probably all heard it, which is about the drunk person who's looking for their keys. You've heard this joke, right? They're looking for those keys under the light. There's the light. They're looking for their keys. Their friend comes over. They look for like 30 minutes. Finally, the friend asks the drunk person, "Are you sure this is where you lost the keys?" And the drunk person says, "No, I lost my keys over there." The friend says, "Why are we looking here?" And the drunk person says, "Well, this is the light where the light is. That's the only place we can look." And dark matter is kind of like that. That you can talk all you want about models that have absolutely no phenomenological implications, but that's the kind of thing I tell my kids before bed at night. Dark matter is like this and blah, blah, blah. But if you can't see it, there's no difference between a bedtime story and science. So we're interested in models that have some connection to the standard model that allow us to have some phenomenological consequences. But it's not just because we want to see it. It also allows you to have better ideas about how dark matter was formed. Why is the density of dark matter related to the density of ordinary matter? Can you connect it to the ideas of thermal freeze-out or non-thermal production that we have? And in some of the extensions, even for very, 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 very small couplings of the order of 10 to the minus 12 or lower, there are still physical signals that you can see in experiments. So people are getting very clever at thinking about these things. If you want to think about how you motivate something like this, it could just be that this is how nature is. You also can put in some sorts of extra dimensional framework if you want, where you have a standard model particle and you have a dark sector over here that then have no renormalizable interactions, so you have some extra dimension. There are some brains. They live over there. We live over here. And there's a limited number of fields that can mediate interactions between us. And as a consequence, the types of interactions that we have are very, very limited. So those are the kinds of scenarios I'm going to be talking about. Generally, people refer to these things as dark sectors, dark sector models, hidden sector models, things like that. But before I get into those, let me talk about one which is a little different from those, and that is Z primes. Okay, so whenever you want to talk about the interactions of dark matter and the standard model, people often refer to this idea of portals. And I'll be a little bit more concrete about what that is in a second, but for the moment, let me just take that as a word. So the first thing is that if you're thinking about non-traditional models of dark matter, the first thing you might imagine doing is simply saying, well, let's imagine that I'm going to give the standard model some new gauge charges. Right? The idea of a WIMP, the capital W WIMP, was something that had capital W weak interactions, W bosons, Z bosons. That seems like that's probably not a good explanation, although it's still possible. And now weak interactions come to mean like Higgs type interactions and things like that. But if you move the next step would be, well, let me start adding new interactions and let me charge both the standard model and the dark sector under that. So this is not really in this framework here because I'm really saying that there is a gauge field that we talk to strongly and that the dark sector talks to strongly. So you can imagine that there's some U1, or generally just a group G under which dark matter is charged. And so then you'd say, well, how can I have the standard model be charged under it? Well, probably what you would do is the sort of most direct thing that you would imagine doing is you could gauge a symmetry or an approximate symmetry of the standard model. So that would be something like, gauge baryon number, gauge lepton number, gauge baryon minus lepton number. You could gauge a flavor symmetry, especially lepton number symmetries. The popular one people like to gauge is mu minus tau. So you could gauge any one of these things. Some of these things have anomalies. Some of them will be anomaly free. If there have anomalies in them, then you have to add additional field content to make sure that's all fixed. But this is sort of the first thing that you can do is sit down and say, let me imagine that dark matter is carries this Z prime, standard model carries this Z prime, and you build such a model. You imagine that this theory is Higgs, so you have some Vev of some field phi under whatever this, I should put G here, which is charged under this group G, acquires a Vev, it breaks it down, and that gives you a Z prime. If you have that Z prime, then everything that you think about ordinary WIMPs carries through. Dark matter can freeze out into standard model particles. The cross-section for this goes like the coupling constant squared times 1 over the Z prime mass to the 4th times the dark matter mass, assuming that the dark matter mass is less than the Z prime mass. So you can take all of your ordinary intuition. It's very easy for this to have a size which is of the order of 1 over 10 TeV squared, which is what you want to have it be thermal dark matter. And so these sorts of models end up being very WIMP-like. The Z prime in general has to be fairly heavy so as not to, if it has order 1 couplings, has to be very heavy so as not to be in conflict with experiments. Dark matter is then also very heavy. The annihilation processes are into standard model fermions. It has all the ordinary thermal properties. And so all the same things that you think about for WIMPs carry over to this kind of a dark matter particle. So why am I talking about it? Well, I'm talking about it because there's also one variant about it that I think is worth noting as one is thinking about dark matter model building. And that is that this restriction here of limiting yourself to baryon number, or lepton number, B minus L, or so on, is a very, very restricted one. If you're talking about light mediators, where things are down at the sub-GeV level, then it's pretty important that you want to keep in mind what the actual symmetries are of your theory. But if you're talking about a TeV scale or 2 TeV scale gauge boson, then this question of what the actual symmetries are is, to some extent, irrelevant. Why is that? Well, the only reason that you care about making sure that all the charges cancel out and all the anomalies cancel and yada, 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 is because you have some idea of what the UV physics is and that the theory needs to make sense as a quantum field theory. And that's because it's a gauge theory. And gauge theory is supposed to have all sorts of consistency conditions and ward identities and things like that. But if you're living in the universe that we do, where we're below 2 TeV or 1 TeV or whatever the mass of the Z prime is, then you do not live in a universe that has an intact gauge symmetry. So from your point of view, as an effective field theorist, because you're all reasonable people and all reasonable people are effective field theorists, then you do not see a gauge symmetry. And if you do not see a gauge symmetry, there's no reason you need to worry about things like anomalies and things like that, because you live in the infrared. And that means that effectively, if you want, you can imagine that the standard model fields have whatever willy-nilly couplings you want to this, and dark matter has whatever willy-nilly couplings that you want to it. It's not that hard to realize that. And if you want to have a UV understanding, this goes by the name of an effective Z prime. And so the way you should think about it is like this. In the standard model, you have the standard model fermion fields that you can write as all left-handed fields, right? Sorry, that's U conjugate, D conjugate, right? So these are the chiral fermions that make up the standard model. So, right, you pair these things together to give the up quark, these things together to give the down quark, these things to give the lepton, and the neutrino lives in there. And you have obviously 3 generations of this. And so what you can do is you can imagine adding, just as an example, you can add to this a field U and U conjugate, where U conjugate has the same charges as little u conjugate, and capital U is the vector conjugate under all the gauge transformations. So this is a 3 bar undercolor. This is a 3 undercolor. This has hypercharge minus a sixth, or sorry, a minus 2/3. This one has plus 2/3. But then on top of that, you also add, say, plus and minus 1 charges under this U1x. Okay? So you go ahead and you write down, you add a field like that to your Lagrangian. So you've got a gauge field, U1x. I've added 2 new fields that look just like copies of up, and then have an additional charge like this. Because these fields are vector-like, you can add into your Lagrangian a mass term like that. But if you have your Higgs field, phi, which is going to break this gauge symmetry down, you can also write down phi times u times little u conjugate. Okay? So what then happens, and you can do this in 2 ways. Both of them mean the same thing physically. You can do this in 2 ways. The first thing that you could do is say, well, I want to integrate out the u quark. And if you do integrate out the u quark, then you can end up with interactions that look like this. Right? Where I've got a covariant derivative on phi. This is a higher dimension operator, right? So I've got this has got to be suppressed by mu squared. But when I put in the vev for phi here, what does that look like? This looks like v squared over mu squared, z prime mu, u conjugate, sigma mu, u. Right? Oh, sorry. That's a conjugate, dagger. All right? So the point is that you have a higher dimension operator that when you actually put in the vevs ends up looking like an effective gauge interaction, right? This is the same interaction that you would have had in a covariant derivative for this thing. It's just not appearing in a covariant way because you no longer have a gauge symmetry. The other way you can think about this is instead of directly integrating this thing out first, what you can do is you can imagine saying, well, let's suppose that I do this in the other direction where I keep my mu scale below the scale of the z prime, and so I want to understand how this then operates in that language. Well, what happens there is that, speaking very loosely, you have 2 right-handed fields, the u conjugates, and 1 left-handed field. Right? You know a Dirac mass is marrying a left-handed field to a right-handed field. Right? So here you have both big u conjugate and little u conjugate that are trying to marry off against u, but you can actually only marry 1 linear combinations of those. Right? Because it's 1 it's one left-handed field. So it can only marry one right-handed field. So there's some linear combination of capital U conjugate and little u conjugate that is marrying U, capital U. And there's one linear combination that's orthogonal to it of little u conjugate and capital U, which does not marry it, and that one is massless. Right? So you say that you've got U heavy, which is U cosine theta, sine theta U conjugate, and I have U light, which is U conjugate sine theta plus cosine theta U conjugate. All right. So U heavy, this is the one that has a Dirac mass to U. And this one has no Dirac mass to U. And you can work this out, right? It's a 1/2 matrix. So 1/2 matrix is very easy to diagonalize. But this degree of freedom here, U light, now is not, this degree of freedom here, which is massless at this level in the theory, is going to have Yukawa interactions. It's going to marry off against Q later on. This light field, this thing which is massless at this stage of the theory, is what you identify as the physical up quark, right? Because that's what appears in your low energy theory. But that physical up quark actually carries within it a component of this heavy field. And since that heavy field had interactions to the Z prime, that massless field that you have now has interactions with the Z prime. Which means, but you can see that the couplings are dictated by this mixing angle, and this mixing angle is just the ratio of this VEV times that mass, right? Times a Yukawa coupling. So the couplings of this light field are, at a theoretical level, can be whatever you want. They're not dictated by gauge constraints or anomalies or anything like that. So if you're living in the effective theory, then the interactions between dark matter and standard model can really be whatever you want. And that's important because if you look at plots from the LHC, they make certain assumptions about what the properties are of the gauge boson. They say, I'm going to assume that the gauge boson has this couplings to matter, and the limits depend intimately on what those couplings are, right? If you're talking to up quarks, it makes a very big difference than if you're talking to charm quarks, than if you're talking to top quarks because of who actually lives inside the proton, right? Or if you don't talk to quarks at all and you only talk to leptons, then you get constraints from indirect detection because your dark matter annihilates to leptons and you go see that at AMS or something like this. So it's just a lesson. The upshot of this is that as you're looking at models and thinking about things, really anything that you want to achieve phenomenologically in terms of the dark matter couplings to standard model fields is really possible. You can really do whatever you want. Questions about this? Okay, so I called that the Z prime portal, but that's not a portal in what most people would mean when you talk about portals. So let me talk about portals. So portals goes to this idea where you've got a standard model sector and you've got a dark sector, and you want to know how they're going to talk to each other. And if you're operating under the assumption that the dark sector carries no fields that have standard model charges, and the standard model has no fields that carry charges under the dark sector, then what you're left with is that you want to include in your Lagrangian operators that are product operators that look like this, right? So you have some composite operator of standard model fields of whatever dimension. You have some composite operator of dark sector fields of whatever dimension. And it's expressed by whatever scale you need to give this whole thing dimension 4. And that's your portal. This is what people mean when they talk about a portal. This operator is the portal. Okay. Now, obviously, kind of portals you can have depend on what lives in the dark sector. But we know what's in the standard model, so we're pretty good at categorizing the portals from the standard model point of view. And because we've all learned, right, that the lowest dimension operators are typically the most important ones, most of the work that's undergone has gone on in thinking about the renormalizable portals of the standard model. Okay? So there are 4 operators, which fall into 3 categories, which are the portals of the standard model. So They are okay. So you have the first one, which is called the gauge portal or the kinetic mixing portal. And so what you have is you have the hypercharge field strength tensor B mu nu times a dark sector U1 field strength. So if the dark sector has a U1, this is an operator that you can write down, right? Because each of these ones is individually, if these are U1s, these are each individually gauge invariant. So their product is Lorentz invariant. And you have this small parameter epsilon out front. This cosine theta weak here is there so that when you go down to low energies, this has the appropriate normalization, because at low energy you think of this as not dark sector mixing with hypercharge, but dark sector mixing with electromagnetism. And so that cosine theta weak is just a convention. This operator here is the neutrino portal, also called the lepton portal. Here, L is the standard model SU2 doublet. H is the standard model Higgs doublet. And the idea is that N is a non-standard model field. So it's some dark sector singlet field. Okay? That one is very, very commonly known to you because, of course, that generates a neutrino mass when you put in Higgs Vev. But there's also more stuff you can do with it, and we'll talk about that. The last one is called the Higgs Portal. The Higgs Portal has two forms. So here, phi is some dark sector field. H is the standard model Higgs field. So you got phi dagger phi, H dagger H. But you also have A phi, H dagger H plus Hermitian conjugate, where A is just some number. Now these are both Higgs portals, but they do different things. This is the renormalizable Higgs portal, and this is the super renormalizable Higgs portal. And I'll talk about how they work in a second. Okay. So most of the interest of these types of models currently is to say that, well, a lot of the interest in this is in the context of going to mass scales which are below the WIMP mass scale. And the reason for that is, in part, if you think back about the range of scales that we talked about for thermal dark matter, you had 100 TeV up here, which was the unitarity bound. Then you had KeV and MeV, which were both different types of cosmological bounds. The MeV bound was sort of a soft cosmological bound. And then up here you had WIMPs living at sort of the 10 GeV to TeV-ish range. And it was realized that for very, very light, weakly coupled particles, those things have not very well been tested. They're not well tested at direct detection experiments because they're too light and they don't deposit energy on things that you would see. If they're very weakly coupled, they can fall into backgrounds at collider experiments. And you have to worry about cosmic rays, as Tracy explained, that there are these cosmic ray limits that below 10 GeV will exclude these particles. But still, as I also explained, there are ways to get around that from a model building point of view. So this is sort of the range of interest. Okay, so this is where people are kind of wanting to look. And this is what people usually mean when they say light WIMPs or just light dark matter generally. So if you go into that regime, then you're typically in a regime where usually, but I'll describe the exceptions, you're talking about adding dark matter to your theory and then including a very, very small coupling here. Because if you have a particle which is 1 GeV in your theory, it better not have an order 1 coupling to the standard model. 1, because you would have discovered it, and 2, because you would have just called that part of the standard model when you discovered it in 1973, right? So these are all beyond the standard model dark sector particles, and the assumption is that these things are small. So, so in these mediator type models, let me just sketch out what are some of the important effects that you see, okay, before getting into the details of the models. First out, freeze out now has two possibilities. Okay. So the first point is that if you have a field that, for instance, maybe mixes with the Higgs boson here, or possibly mixes with the hypercharge there, and it picks up some interactions with standard model fermions, then it can typically, that sector over there, which talks to that particle, can be kept in equilibrium through a process that looks like this. So you have your hidden sector particle. This could be a scalar or a vector that is absorbed by a standard model fermion, and then you emit a photon. And that even with a very, very small coupling here, because you're comparing this to the Hubble rate, and the Hubble rate is so small, this is often very, very easy to keep it in equilibrium, even if this coupling is down as small as something like 10 to the minus 8 or so. This can be very efficient at keeping this in equilibrium. Then the freeze-out story is a little different, because you kind of have two options. The first option is where dark matter can annihilate into this state phi, and then phi stays in equilibrium with the standard model through this process. That's very wimpy in the sort of traditional sense, in that you have some process, it's annihilating until this process freezes out, but this is what's maintaining equilibrium with the standard model, right? So chi is in equilibrium with phi is in equilibrium with f, and that's how this works. This cross-section then typically goes as something like alpha squared over m chi squared, all right? Because this, where alpha is set by this coupling here. So if you want that to be TeV, then either you need to have a theory where that coupling is very, very small, or that mass is roughly TeV, okay? So this kind of a scenario where dark matter is annihilating to these is typically more common in situations where the dark matter is also WIMP-like, 100 GeV, 200 GeV, 500 GeV, because then your cross-section is naturally 1 over TeV squared, okay? Which is what you want to have a thermal dark matter. In contrast, this sort of a scenario here very naturally lends itself to being light dark matter. One of the problems of light dark matter is that if you think about your cross-section, and your cross-section goes something like 1 over the dark matter mass squared, and you're thinking about dark matter that has a mass which is a GeV or 100 MeV or something like that, you know that that cross-section is orders of magnitude too big to give you the right relic abundance, right? You want something which is suppressed by the TeV scale, not by the GeV scale. So you want your theory to sort of naturally give you some additional suppression mechanism. And so what often happens here is that even though dark matter has an order 1 coupling, you have some small parameter, which is coming from a mixing term, which suppresses this. And as a consequence, this interaction goes like E squared over m chi squared. And so as you make, epsilon squared over m chi squared. So as you make epsilon small, it's also natural to have the dark matter mass be small. In some theoretical models, the mass scales of the dark sector actually do scale down as you scale down epsilon. So it's actually very natural to often have both of these things becoming small at the same time. But this is something that any sort of light dark matter model which is in thermal equilibrium needs to address, which is if my characteristic mass scale is 1 over a GeV, y squared, why is my cross-section 1 over TeV squared? And these sorts of dark sector models with small mixing terms naturally give that. Next. Right, so right now I'm still talking generically about these sorts of mediator models, and we'll get into the details in a second. Interestingly, you might think because you have this small mixing that the direct detection cross-section would also be very, very small, right? Because just like the annihilation cross-section is suppressed here, you'd say, the direct detection is suppressed there. But the process is different because the mass scale that's characterizing this process is the mass of the dark matter, whereas the mass scale that's characterizing this is the mass of this intermediate particle here. They can be different, but even if they're the same, what you end up with is a cross-section which goes like epsilon squared over m phi to the fourth, right? And so even if this is only weak scale, this thing here can be larger than weak scale. It can be weak scale or larger than weak scale, just because this mediator is so light. Okay? And this is actually a natural scenario thing that you find in these sorts of light mediator models, which is that, yes, you've turned on this small mixing parameter, but because scattering processes are not very hard processes, they can be enhanced by this light mediator mass. And as a consequence, you can have very, very significant cross-sections for direct detection experiments. Likewise, scattering processes through this light mediator of dark matter on itself can also be very large. If you just look at this naively, you would have said that this process should be something like 1 over m phi to the fourth. But actually what you need to do is you need to look at an effective average cross-section. The effective average cross-section is dominated by the lowest mode scatters. So oftentimes the total cross-section of dark matter at very low velocities is just set by 1 over m phi squared. Okay? So effectively, if you think about it, dark matter is coming along with some Coulomb field around it, and at very, very low velocities, if these things enter into each other's Coulomb fields, they scatter. And you can think of that as approximately hard sphere scattering with a size set by the Compton wavelength of the mediator particle. But the point is that this is a large cross-section. Okay? If this is weak scale, then this is bigger than weak scale. So you can end up with models of self-interacting dark matter as well. So as a consequence, these types of mediator models, even though you think you've hidden the dark matter away in some hidden sector, actually can have large indirect detection signals, they can have large direct detection signals, and they can have large dark matter signals. The thing that they typically don't have is very large collider signals, but we'll discuss that as well. So let me start with the Higgs portal. Now the Higgs portal, remember, is actually two operators. So let me take them in turn. There's a classic paper where a lot of this is worked out by Burgess, Pospelov, and Der Feldwy. I don't have the archive number, but they only wrote one paper together. And so what they did is they said, look, just take this operator, which has some coefficient. I can go ahead and then add in a mass squared for this dark matter particle as well. And then when I give a Higgs of Ev, then this operator here gives me a correction to the mass. Plus I get a trilinear term. Plus, of course, I get this residual quartic term. Okay. I mean, this is still phi dagger phi, h dagger h. Well, that's actually now h squared. That is h squared. So this means that you now have freeze-out processes. Sorry. Let me try and keep my dashes and dots consistent. We use dots for dark matter, dashes for the Higgs boson. So if I have this dark matter particle phi, which is below the mass of the Higgs boson, then my dominant annihilation process is to go through an S-channel Higgs into standard model fermions. And if I'm heavier than the mass of the Higgs boson, then I also have the ability where I can annihilate into Higgs bosons. And what's nice then is that the only coupling which is dictating your thermal freeze-out is this coupling lambda here. So you can go through and you can solve the Boltzmann equations and figure out precisely what value of lambda you want. That lambda then can be translated into an observable quantity, namely the direct detection signal. Because if you know lambda, then you know the size of this trilinear coupling. And if you know the size of the trilinear coupling, then you can take this diagram here, rotate it, and you have standard model scattering off of nucleons. Okay? So their very, very good and simple point was, once you know freeze-out, you know what the direct detection cross-section of this is. And what they found was that for m bigger than about mh over 2, you had a cross-section of 10 to the minus 45 squared, which is in the vicinity of what current experiments are. Current experiments are a little bit better than that. And in the light window, then you had cross-sections which were typically bigger than 10 to the minus 44 centimeters squared. Now, these sorts of models typically end up being very, very WIMP-like. And the reason that these things end up being very, very WIMP-like is that if you try to move this particle down in mass, well, obviously if this has a mass which is comparable to the Higgs, then it's got order 1 couplings to the Higgs, it's annihilating to Higgses, it's a WIMP, it's just a basic WIMP. As you start moving the mass down, then the only annihilation process is into standard model fermions. But if the annihilation is into standard model fermions, then that means that you're taking a hit because you're becoming suppressed by the standard model Yukawa coupling here, which is getting smaller and smaller the lighter you're becoming. Once that gets very, very small, you now have to keep this coupling here pretty large in order to compensate. But if you keep this coupling large to compensate, then that means that this correction to the mass term, which is just lambda times v squared, is big. Okay? So you make dark matter light, the coupling to standard model fermions drops, you need to increase the coupling of this thing to the Higgs to compensate. That ends up being a somewhat more tuned theory, because now the mass of this is being set closer to the Higgs mass scale. Now you can use the renormalizable portal, the super renormalizable portal, I should say. So what does the super renormalizable portal do? Well, you put this term in your Lagrangian, and what happens is that you put in a VEV for one of these Higgses, and that causes a mixing between this singlet S and H. Okay, so here S, sorry, is my field. I'm distinguishing S from phi because phi is dark matter. Phi carries a Z2 at the very least. Here S doesn't have any quantum numbers, any preserved quantum numbers, so it will decay. It can't be dark matter. So dark matter has to be something else. So if dark matter is something else, then you can add couplings of, say, a fermion or a scalar to this singlet S, and then you're back to this question of whether you're annihilating like that or whether you're annihilating like that. If you're annihilating like this, then you have to put in a mixing term here where this dark matter talks to the S, the X then mixes to the Higgs boson, and then the Higgs boson talks to the Fs, to the fermions. If you work this all out, this whole thing then is 1 over ms squared times this mixing term times 1 over mh squared. What ends up happening is that this ends up essentially canceling out if you want to have a natural theory, and you end up with a quantity which is just basically going like 1 over m Higgs squared. So these things tend to be very, very suppressed when you have their freeze out. So these tend to be hard models to get to work if you want them to be very, very light, just because they take this big hit from the Yukawa coupling. So there's not as much work on these sorts of models. Most of the work is on the next category of models, which are kinetic mixing models. So this is the kinetic mixing portal, or the dark photon portal. So we heard actually quite a bit about this at a pretty nice level yesterday. We heard all the searches about all the searches going on here. So this is a very exciting field. And before I get into this too much, the searches that are being done here, the searches that are done at SLAC and Bell, Babar, JLab, things like that, I think it's worth noting that in about 2008, there were very, very, very few constraints on this idea of dark photon. There were some long-standing limits from Precision Electro Week. There were some long-standing limits from beam dump experiments that had happened previously. But there's been tremendous progress made in the last decade. The reason I bring that up is that a lot of that progress was really driven by young people. And I mean people who were in their first postdocs, coming up with ideas of how to test these things, going to the experimentalists saying, here's an experiment that you should do, helping write proposals and driving it. So I'm thinking of people like Reuven Essig, Natalia Toro, Philip Schuster. These people were very, very active from early on in thinking about how to test these things and did that. So I want to emphasize that it's not just that we've made progress in the last 10 years, but that progress was a direct result of some of the youngest people in the field coming up with creative ideas and pushing them. And it's because of them that we're where we are today. Them and, of course, massive amounts of experimental efforts and tremendous work on the experimentals. But really, I think the initiative of a few active researchers led to a lot of what we see today. That's an aside. That's just trying to motivate you to remember that you can really have a big impact if you carry your ideas forward. So, at low energy, you can write your Lagrangian Okay, so I'm now imagining I'm going down below the scale of electric symmetry breaking, so I'm really talking where my leftover massless fields are the dark sector, U1, and the standard model electromagnetism. So I have my ordinary kinetic mixings, and I have my ordinary field strengths for electromagnetism, and I have my field strength kinetic term for dark matter, and then I have this kinetic mixing term proportional to epsilon. And so you have this off-diagonal term in your mass matrix, or in your kinetic energy term. And so what you want to do is you want to go to a basis where your terms are diagonal, right? So what do you do? The easiest thing to do is to replace wherever you see your electromagnetic field. You replace it by A mu EM plus epsilon dark, or epsilon alpha A dark. That then you'll find kills off this mixing term. You then have to do an overall rescaling to get yourself back to canonical normalization. But at leading order in epsilon, this is all you need to do and you're done. Everything else is higher order in epsilon. If you do that, what happens? Well, if you think about the kinetic terms of your standard model fields, where they have initially this interaction with the ordinary photon proportional to the electric charge and the charge of the field, that then gets replaced by, this is E A mu slash plus IQ E epsilon dark. So before, I had a coupling to the ordinary photon, which is proportional to my charge and the coupling constant of EM. And now I have that plus an additional interaction to the dark photon, which is proportional to my charge and the electromagnetic coupling constant and epsilon. Okay? So this tells me that when I do this diagonalization, I've now picked up this tiny, 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 tiny interaction with that dark photon field. Now, you're looking at this, And a very, very reasonable person, which you all are because you're effective field theorists, would say, why are you shifting the standard model photon? Why not shift the dark sector photon? And the answer is, at this level of the theory, you of course could. I didn't have to do this shift by shifting the standard model photon. I could shift the dark photon by epsilon. I would exactly cancel off the same thing. But if I shift the dark photon, then I don't do this replacement here. The standard model photon stays the same. So what's going on? What's going on is that at this level of the theory, I haven't given you any reason to choose any special basis. Indeed, the only special basis that is in this thing here is the basis where you can talk about the gauge field that talks to standard model stuff. Right? That is a basis. You can choose that direction in field space. There's one direction in field space, which is the direction that talks to standard model stuff, and there's the perpendicular direction. And the thing that talks to us, that's what we're going to call the photon, and the thing that's perpendicular to us, well, we don't talk to it, so who cares, right? That's just something else. But that's only at the level of this, right? If I extend this theory by, for instance, adding a field phi, which requires a VEV, which is charged under this initial dark sector, then you now have a different basis which is special. Because you have the basis of things that talk to us, and you have the basis of things that talk to them. And those two bases are not orthogonal, right? Because of this mixing term. So now, actually you can make the argument that this is the important basis to choose, because this is the basis that chooses something that gets a mass, right? Phi gets a VEV, so whoever it talks to is going to be massive. The thing which is orthogonal to it will be massless. And the thing that is massless is what we will call the photon. Because what we mean by photon is not actually what we talk to. What we mean by photon is that thing which mediates very, very long-range interactions between electrons. Right? So if phi gets a VEV, it gives a mass to one linear combination. And the orthogonal linear combination is what we call the photon. And if you do this, then this shift is the one you want to do. Because if you do this shift, then phi, with its covariant derivative, will still be in the usual form. So when I put a VEV in here, I'll give a mass to precisely that field. Right? So, put another way, diagonalizing it this way is the way in which I have left it as the basis of the thing which I call A dark is the thing that acquires a mass. Okay? And that's the basis you want to work in, because mass eigenstates are often the nicest way to work. There are some important exceptions where you want to be careful about what you mean by the photon, especially if you start doing experiments that are at distances shorter than this mass. But in most cases, this is just the right basis to work in. You have a dark photon, which talks to the dark sector, and you have a dark and the dark photon also talks to us, proportional to epsilon. And then we have ordinary couplings to the photon. Questions about this? Yeah. This is the low energy effective Lagrangian below the scale of electroweak symmetry breaking.
Because I was just wondering, because there's no scale in the Lagrangian which mediates it.
Oh, in this Lagrangian right here? Yeah. Well, this Lagrangian I was writing down sort of before I. Do you mean what do you mean mediates it?
I think for me, it's an effective Lagrangian. It's always with some scale.
Some cutoff scale.
Yeah, some cutoff scale.
Yeah, yeah. So there is a cutoff scale here. I mean, the cutoff scale here is really just the weak scale. I could have embedded this into the full standard model, where I just wrote down standard model times a U1 dark with this kinetic mixing term, and that would have been a perfectly good theory all the way up to the Planck scale. Right? There's nothing wrong with that theory, up to the usual hierarchy problems. But as an effective theory, there's nothing wrong with that up to the renormalizable theory. I can do whatever I want. So, but the only correction going from the standard model to here is that I've replaced hypercharge by F mu nu. And that's just because typically when people are talking about this, they're talking about very small mixings and light fields. And by light fields, people usually mean below 10 GeV. Okay? Other questions about this? Yeah.
So I can also generate this coupling term by giving standard model field charge under this U1 dark, right? Then at loop level you will generate this.
Oh, if I give standard model fields charge under this dark sector, first off, then you have to go back and make sure you're doing all the things about anomaly cancellation and yada, 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 right? But then you don't need to think about this epsilon at all, right? Because I already in my covariant derivative have plus q g dark a d slash, right? So that's a situation where the standard model fields have order 1 charges to the dark sector. So usually we want to think about situations where the standard model has no charges to the dark sector at some leading order level in the theory. But it is true that if I add just heavy fields that are mixed in charges, then you can generate this radiatively. And then that will be suppressed by 1 over 16 pi squared because it's a loop. Possibly it will be log enhanced because it's running. But it can also be a threshold correction. You can also have it come where this is coming out of a non-abelian gauge group, which has some additional symmetry breaking that can come at another loop level. So you can make this 2 loop. I can tell you theories where you make this 3 loop. So this is generated naturally at loop level, and there are totally reasonable theories where this is generated at 1, 2, and 3 loop level. But if you kind of imagine a situation, if you just, as a sort of phenomenologist, what I think a lot of people do is they just step back and you say, like, I know it's not order 1, because I would have seen it. Like I said, then you'd call it the standard model. So it could be small, and I should just try and consider a whole range of what I can detect in terms of small.
So, but when you shift this standard model photon to this shifted photon, doesn't that mean you are giving a charge, dark charges to the standard model photon proportional to the epsilon?
Yeah, when I do this transformation, all standard model fields now have epsilon charge under the dark photon. That's absolutely right, and that's the critical feature of these theories, that you end up with all standard model fields have charge which is proportional to epsilon. It's proportional to their standard model charge times the standard model coupling constant times epsilon. That's what their coupling to this new gauge boson is. Other questions? Yeah.
Do you also expect some dark sector particles to be coupled to the standard photon with charge epsilon?
No, and that's the critical thing about this diagonalization, right? Which is that if I imagine, right, if you think about this field, forget about the fact that I'm giving it a VEV for the moment. I could have, and in fact I do often have a field right? I do have a dark sector field. Remember, I had a choice of how I diagonalize this, right? And I diagonalize this by shifting the standard model field, not the dark sector field. So these dark sector fields didn't pick up epsilon couplings to the photon. And there was a physical reason for that, right? And the physical reason for that is that assuming that all the dark sector fields have the same alignment of their charges, and all the standard model fields have the same alignment of their charges, which is to say that we start off all coupling to the same gauge field on one side, and they couple to the same gauge field on the other side, and the only thing that connects those things is this epsilon. Then the thing that gets a mass is the thing that talks to phi, right? But chi talks to the same thing that phi talks to. So chi only talks to the massive eigenstate. Chi does not talk to the massless eigenstate. So as a consequence, these dark sector fields do not, in general, pick up epsilon charges under electromagnetism. We pick up epsilon charges under the massive photon, but they do not pick up epsilon charges under the massless photon. It's actually surprisingly challenging to write down a nice theory where you spontaneously generate a small electric charge for dark sector particles without putting in the small parameter by hand at the beginning. Other questions? Okay. So what I'm going to ultimately do is I'm going to imagine, at this point we've just written down a gauge field, we've Higgsed it. What I want to ultimately do is add to this thing dark matter. But before I do that, you can start asking the question, well, what about this dark photon? Could it be dark matter? And why not? So if this dark photon is heavier than the electron, then it will decay to 2 electrons and will decay with the width which is proportional to the mass of the dark matter times epsilon squared, which if it's heavier than the electron is like MeV times epsilon squared. And remember, the age of the universe is 10 to the minus 33 EV. So if you want its lifetime to be less than 10 to the minus 33 EV, you can very quickly see that you need to have very, 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 very small epsilon. So it's easier if you take the dark photon below the electron mass and then ask what happens. And what happens then is you have loops of electrons that give you a decay into 3 photons. And this has a width which is proportional to alpha to the 4th, which is a small number, 10 to the minus 8, which is a small number. But then you also have this m dark photon to the 9th divided by me to the 8th suppression factor, which means that this very, very rapidly gets long-lived as you lower the mass of the dark photon. So once you lower the mass of the dark photon below about a keV, you get to cosmologically long lifetimes. Now, it turns out that it's not just, you can't just have cosmologically long lifetimes, because if this thing is decaying into 3 photons and it has mass around a keV, then that's spitting out all sorts of X-rays into the universe that even if it's lived the age of the universe are excluded. So epsilon needs to be very, very strong for a variety of reasons. But basically below about a keV is where people start talking about this as dark matter. And this is dark photon dark matter. Now, unlike thermal dark matter, which sort of naturally suggests to you a means of formation, there is not an automatic suggestion of how to produce this dark matter very naturally. The best, I would say best, the idea from my perspective, which I find the most interesting, there are many ideas. You can come up with an idea, maybe it will be more interesting. But the best idea that I like is by Graham, Martin, and Ragendran, where they suggested that if you have this very, very light field in the early universe, then during inflation, in inflation, all massless fields oscillate. So you have particle production during inflation of any field which is massless, including this dark photon. So if this dark photon is there, then it should be produced during inflation, and you can ask what kind of a relic abundance you would get from those inflationary production. And what they find is that the energy density compared to what you want depends on the inflation scale. But if you have very high scale inflation, so the highest scale of inflation, this is the Hubble constant during inflation, the highest scale that is currently consistent with the data is about 10 to the 14 GeV. So if you have the highest possible Hubble constant, then the mass that you'd want to get the right amount of dark matter is about a few times 10 to the minus 6 electron volts for your dark photon. And then as you lower the Hubble scale, then you increase the mass of your dark photon to get the right amount of stuff. There are a lot of limits on this. And I'm going to draw a terrible, terrible plot because I was not hired for my art skills. But I will do my best. So this is not to scale, obviously, because this is 10 to the minus 12 eV, this is 10 to the minus 6 eV, and this is keV. But so if epsilon, so this parameter here is epsilon. This is the mass of the dark photon. So down below keV is the mass range you're talking about. If you live up in this region here, this particle has enough interactions with ordinary matter that it cools stars too efficiently. if you're in this range of parameter, then this is a 10 to the minus 6 EV particle and lighter, which means this is going to have effects on atomic spectra. So just the experiments you do of precision atomic spectra and electroweak studies can constrain this. In these two regions, you have effects on the CMB, either from production of these dark photons from CMB photons or production of CMB photons from these dark photons. And then over here, there's a small limit of a constraint from xenon 10 from the absorption of this into their electrons. And so, sorry, this limit is like this. It starts at like 10 to the minus 9. It goes down to 10 to the minus 12. So this is the range of parameters that you're talking about. Okay? Sort of in this 10 to the minus 12 and lower. So this is a very, very small epsilon that you're talking about. It's a very, very small mass scale you're talking about. But it's still an interesting model to consider because it's pretty simple. It's got these small, very small numbers in it that you just put in by hand. But it's a very simple scenario. And it's interesting because you now have a particle that you can look for in its effects on precision atomic phenomena, or by looking at its absorption into direct detection experiments. Yeah?
What was omega v?
Oh, this is omega v. This is the amount of, so omega is the phrase, the term we usually use for the amount of dark matter divided by the total dark matter. And so this is the energy density in the vector. So people refer to this as vector dark matter, or so some people call it dark photon dark matter, some people could just call it vector dark matter. And so this is the versus what we measure. So this is theoretical value versus the observed value of omega dark matter. So this is the statement that if you want this scenario to give you the right number, this whole thing should be equal to 1.
If you only have dark photon, yeah, without any other dark sector.
That's right. Okay. So.
Sorry, how does xenon constrain it?
Xenon constrains it because what happens is that the dark photon comes in and it gets absorbed by an electron. And so you see an electron recoil. And originally, xenon 10 didn't do an analysis of this, but and I think Brian Battelle will tell you about these experiments next week. But Martin, Volansky, Essig, and Sorensen went back to the xenon 10 data and reinterpreted it in terms of constraints on electron absorption. So usually the direct detection experiments are built around looking for nuclear recoils, and their backgrounds are electron recoils, but they're still good at seeing electrons. They just have a lot of background there. But because this thing is so light and there are so many of these things, and because this thing talks directly to electrons, it can just come in and be absorbed by an electron and kick it out of the nucleus. Kick it out of the atom, excuse me. There are no electrons in the nucleus. Okay. So that's if the dark photon is dark matter. Let me now shift gears and imagine that I'm going to extend the dark sector by adding in another field. Okay, so I'm going to add in some fermion field, which is charged under this. So I'm adding in chi, which is charged under the U1. And then you have precisely those sorts of freeze-out scenarios that I discussed. If dark matter is heavier than the dark photon, then you have hidden sector annihilation. If dark matter is lighter, you have standard model annihilation. As I was saying before, since this doesn't have any small parameters in it, this doesn't know about epsilon. This is typically more common for heavier dark matter models, like weak scale. Because this one has this small epsilon parameter suppressing this annihilation, this is typically more common for light dark matter models. Now, if you want to think about these light models, then one needs to be a little careful because you need to extend the theory just a bit. because, as we said, if this is annihilating into, if I've got a 1 GeV particle annihilating into, say, electrons and muons, then the constraints from the CMB are far too strong for that to be allowed. So you need to somehow have this process allowed in the early universe, but forbidden at late times. And then what people usually do to solve that is either you replace the fermion by a scalar. If you have a scalar, then the annihilation is naturally p-wave. So scalar annihilating into fermions is a p-wave process, so it's suppressed by velocity. Or you add to the theory. So if you have this mass term in your Lagrangian for this field chi, you can add to it an operator, something like this, which is a Majorana mass term once phi gets a VEV, that will take this Dirac fermion and split it into two pseudo-Dirac states, right? Or if phi has charge 2, then you can just go ahead and write down a renormalizable term like that, right? Because the assumption is that chi has charge 1. Sorry, not this. This would be this. So that's what you need to do. So we like to say these words like, oh, this is, just has all the ingredients of the standard model, right? It's just the same things. There's fermions, there's gauge fields, there's Higgs bosons. That's true, but you need to go a little bit farther because you need to have 2 types of mass terms for the field to make sure that you do this splitting, or you need to have extra scalars that don't acquire VEVs. So just to be full disclosure there. So what about signals? Well, if you want to turn off the annihilation at in the early universe, the temperature of dark matter at recombination is very, 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 very low, right? The thermal temperature is EV, but dark matter decoupled from the thermal bath long before that, so it's even colder, much colder. So that means that you actually just need a tiny, tiny, tiny splitting, really, for dark matter to turn off this annihilation process. You still can have a direct section signal, or you can have heavy dark matter. And so you can calculate this cross-section per nucleon. And this is what you get. So I'm writing it this way because this thing is coupling to protons only. And when people talk about the dark matter coupling per nucleon, they're assuming that it's coupling to all things universally. So that's why you have these funny things that give you some isotopic dependence. But more or less, this factor is kind of 1. This thing is suppressed by epsilon. So if it's 10 to the minus 3, then you get this. If alpha dark, I'm assuming it's the same as the fine structure constant. Mu NE is the reduced mass of the WIMP of the dark matter and a proton. And this is the mass of the dark photon compared to GeV to the 4th power. Okay? So what this is saying is that for 10 to the minus 3 epsilon, for an alpha dark of that size, and for a dark photon of GeV, the cross-section you get is 10 to the minus 37 centimeters squared. And remember, the current limits are down at like 10 to the minus 45, 10 to the minus 46. So this is a very, very, very big cross-section. So either you need to make this splitting between these states really big so you can turn off this scattering, because this scattering is from the light dark matter state into the heavy dark matter state. Or you need to move this down into the mass range where direct detection experiments aren't sensitive. So that is light dark matter, 100 MeV, where they simply can't see it because the amount of kinetic energy is too low. So this is a thing that you need to worry about for these models, but it's also an interesting thing because it tells you that when you start looking down at light dark matter models that have these sorts of interactions, it's very natural for them to have awfully big cross sections. This is even bigger than the cross section that you have for the Z boson. So that's most interesting for light dark matter, I think. For heavy dark matter models that are annihilating in this way, then the idea there is that you're imagining there's some hierarchy of scales typically. So the idea is that the dark photon mass is GeV-ish, and the dark matter mass is more like weak scale, right? Because you need this thing to have a thermal cross-section. And if you do that, then what's interesting is that your dominant signal is dark matter annihilating into these dark photons. Those dark photons then propagate and they decay. When they decay to E plus E minus and U plus U minus, they end up giving you very, very, very high energy leptonic signals, which is actually one of the original motivations that people started talking about these models, was trying to understand the excesses that we're seeing in things like AMS and other experiments that saw excesses of high energy electrons and positrons. So the first thing of note is that dark matter models like these don't have typical weak annihilations. Typical weak annihilations are often into quarks, so you get lots of pions, lots of photons. Dark matter models like these annihilating into gamma dark, which then decay into standard model fermions. If they're light, you're getting muons, electrons, and things like that. And so you're getting a lot of positrons at the end of the day, neutrinos. There's one other very, very important phenomenon that occurs here, which is that when we calculate dark matter annihilation, what we typically do is the same thing that we do whenever we do any scattering process, which is we're effectively doing the Born approximation, right? Which is where you start with plane waves. Those plane waves come in. There's some interaction term in your Lagrangian. They interact at some point where they overlap. And then you have plane waves that then go off to infinity, right? And that's how you do your calculation. And we convert that into Feynman rules, and you go on from there. But in these sorts of models, there's a phenomenon which is called the Sommerfeld enhancement, which changes that intuition. And let me explain this in just a couple of very, very simple ways. The first way is you can understand why intuitively at low velocities your cross-sections can be changed. And that is, you imagine that you're in outer space, and here's the Earth. And you throw a rock at the Earth, okay? If you throw it at very high velocity, this rock is going to go in a straight line, and the cross-section of the Earth is pi re squared, right? Right? If you kind of imagine that you have a target, that's how big your target is. But if I throw it at very low velocity, then what happens is gravity takes over, and the rock will be pulled down. So there's actually a correction to this that goes like v escape squared over v squared. So if you're throwing this at a velocity which is much lower than the escape velocity of Earth, you get this big, big enhancement, which is just to say that this thing is getting pulled down by the Earth, and it's going to want to hit it. Okay. The same thing happens here, although we don't think of it in these classical terms. The way we think about it is either you can say the following words. You can say that the coupling constant, the process is no longer perturbative in the coupling constant because the actual expansion parameter is something like alpha over v. This is the expansion parameter, not alpha. So at low velocities, you're actually doing a series in alpha over v. And if you look at it, that's what's happening. And so that means that you actually need to sum all these diagrams that contribute. So it's not just the leading exchange. If v gets small, this can become large, and you need to sum up all the diagrams where you have multiple exchanges of this dark photon. The other way you can say it is you can say that that plane wave approximation that you did was a bad approximation. That when these particles came in vicinity of each other, their wave functions were distorted, and so they had a higher overlap, and that enhances the annihilation process. So alternatively, you can solve the Schrodinger equation to find out what the actual, if you start with these low velocity plane wave states, look like when they come into contact with each other, and you can calculate that. And indeed, one of Tracy's early contributions was to do these calculations for these models. She's done a lot of stuff since then, but that was one of her early things, was to calculate that enhancement factor. And this doesn't increase forever, because eventually you become sensitive to the fact that you don't have a massless mediator like gravity, you actually have a massive mediator like this dark photon. So you get an enhancement to your cross-section, which goes like pi alpha over v. So the actual cross-section is this Sommerfeld factor times your nominal cross-section. And if v gets sufficiently low, this saturates at a value of alpha m chi over m phi, when the de Broglie wavelength of your scattering process becomes larger than the Compton wavelength of your mediator, and it becomes effectively a point-like interaction again. But for pi alpha of things like 10 to the minus 1 and v of something like 10 to the minus 3, which is what it is in our galaxy, you can have enhancements which are something like factors of 30, 50, 100. Okay? So this is an important phenomenological difference of these models, because usually you say the cross-section that you want to have for dark matter is 3 times 10 to the minus 26 centimeters cubed per second. But in these sorts of models, actually, the cross-section is naturally much, much larger. These models have some interesting collider signals. And I think this is a nice example of how these sorts of models and these sorts of things interact with experimental physics. Because you can imagine some process, and I won't specify what process, where you're at a collider and you have proton-proton goes to x plus this dark photon. Okay? So you're looking at your beam pipe here, and you've stuff coming out on one side, and then you have this dark photon coming out on the other side, let's just say. And all this stuff is, jets or gauge bosons or whatever. And what happens to this dark photon is that it decays into, say, E plus E minus or mu plus mu minus. And what's interesting about this is that if this thing has a mass, if you imagine that this is produced with a characteristic energy which is of the order of the collider experiment, so 100 GeV, TeV, something like that, then this guy is flying out with an energy of 100 GeV. But this dark photon itself only has a mass of around a GeV. So when it decays, the invariant mass of this pair has something which is of the order of dark matter mass, which is GeV. So if the invariant mass of this system is a GeV, then that means that the transverse energy is pretty small compared to its energy along the direction of motion. So these two leptons are very, very highly collimated. Okay, so they're flying out in a very highly collimated way. And why that's interesting is that at colliders, they typically make isolation cuts on their leptons. If you say you do an experiment where you look for a lepton, they usually mean an isolated lepton where there's nothing in its vicinity, because you don't want a lepton that's inside of a jet, because that would be not what you mean. Jets produce leptons all the time. Usually you're looking for a unique lepton that came out of a W boson or a Z boson or something. So searches for leptons and colliders don't pick this up because they're not isolated. So they had to develop a whole different technique to look for these things, but they got the name of lepton jets because they kind of look like jets in that they have an invariant mass around a GeV, but they're made out of leptons. And this is the simplest case that you can imagine of doing this. The simplest case you can imagine of doing this here. But you can also imagine a situation where you, for instance, have a more complicated dark sector and you produce some particle X, and maybe it decays into two of these dark photons and they decay. So you can have lepton jets and things that have pions, things like that. But the point is that there was actually something that came out of dark matter theorists then talking to experimentalists and saying, oh, there's this new object that should be looked for, and now there are searches for these types of objects at the LHC, which is, even if they're not found, something which is important, because if you don't do these searches the first time at the LHC, it's not obvious that you can go back and do them later because of how the trigger menus work. So what about constraints? Well, we heard a lot about constraints yesterday, and Brian Battelle will tell you all about constraints, a lot of constraints next week. That's the nice thing about not going last, so you can just say, ascribe things. I will send Brian an email later today to tell him what I told them you would talk about. So there's a beam dump experiment called NA64. I didn't put any mass ranges on here. What is this? This is like 10 MeV. I won't put any number down here, and that will make this correct. I'll put a number up here, and I'll put a number over here. So so now I've considered possibilities where there's dark matter annihilating into dark photons, or where dark matter annihilates into standard model fermions through a dark photon. In this case, the dark photon decays to leptons. In the other case, the dark photon will decay to dark matter. So in one case, it's a visible dark photon. In the other case, it's an invisible dark photon. If you have an invisible dark photon, so that is gamma dark going to dark matter when it decays, then the limits are dominated at this point by Babar, which places a limit at about 10 to the minus 3 up to about a 10 to GeV. And down around 10 MeV, MeV or so, and I don't remember what this transition point is, I apologize, you have Na64, which places some stronger limits. If it is a visible dark photon, which is to say it decays into electrons and such, and there's a different plot where I have more numbers. Sometimes people like to do this trick where they plot epsilon squared instead of epsilon, because their limits are much stronger, because the limits on epsilon squared are obviously 10 to the minus 6. So you have various beam dump experiments that constrain you in this range here. Up in approximately this range, you have a combination of Babar, Bell, MAMI, Apex, a lot of experiments. A lot of these experiments here that probe this range are the ones that really got done in the last decade. You also have some future limits. So I'll make these dotted. Doesn't matter, you can look them up. But in this range, you have LHCb looking at decays of B mesons, and an experiment called SHIP at CERN, which will place limits as well. So the point is that these kind of model is basically constrained at the 10 to the minus 6 level for epsilon squared, or 10 to the minus 3 in epsilon. Questions about this? So there's been a tremendous amount of activity in this scenario, but people are still coming up with all sorts of new and clever ideas. There are all sorts of new experiments being proposed, again, dominantly by young people coming up with some idea and saying, if you did X, if you put this Foley detector, near one of the experiments that are already going on, often there are these experiments that you say can run parasitically, which is to say that you put a direct detector in the vicinity of an experiment which is already ongoing, so you don't need to tell them to go and use their beam for something brand new. You can actually use the existing beam in the existing experiment. There are a lot of these parasitic experiments that get proposed. So people are coming up with really interesting ideas all the time. If you have any good ideas, there's a great opportunity to propose them. Okay. I only have a few minutes for the neutrino portal, but that's okay because you've got lots of lectures about neutrino physics. Although I will say that from my perspective, the neutrino portal is the one that has been explored the least, in some sense because it looks the most innocuous, and so I'm spending my own personal time. I'm thinking about this one right now. So the neutrino portal, you write down a Yukawa coupling times the lepton times some singlet fermion n times the Higgs boson. H acquires a VEV, and this gives you a Dirac mass. All right. So you can kind of now go through the process. Let's suppose that n does not have a mass. If n doesn't have a mass, then this is a Dirac mass, and you're kind of done, right? We measure neutrino masses. That's the Dirac mass. That's not the dark matter. There you go. If you then extend this by adding in a Majorana mass, then it gets a bit more interesting because you now have a mixing angle and you have a light neutrino mass given by the seesaw mechanism. So now you're really starting to talk about a dark sector. And this scenario where you've added a sterile neutrino at a higher mass range with a small mix angle is what people usually mean when they talk about sterile neutrino dark matter. That's what I'm talking about. You've been hearing all about neutrino oscillations. And so you can ask the question, how are you going to produce, let's suppose that this is your model, and you would like to make this heavy eigenstate and have it be dark matter. How do you produce it? Well, because of the very small coupling in here, right? So if this mass ends up being KeV, then your mixing angle at the end of the day that you want often ends up being sort of at the 10 to the minus few level. And if you have a mixing angle at the 10 to the minus few level, then that means that the Dirac mass is of the order of a few eV. If you have a Dirac mass of the order of a few eV, then you're talking about Yukawa couplings, which are of the order of like 10 to the minus 9, 10 minus 10, 10 minus 11. Those are very small, right? So this is not going to come into thermal equilibrium from those Yukawa couplings. So you have a variety of non-thermal processes that make this. The most common one, which is known, is called the Dodelson-Woodrow mechanism. Dodelson-Woodrow is precisely what you would have thought of if you started working out the cosmology of this thing, which is that it gets produced in the early universe. It's going to have some probability to transition into a standard model neutrino. Or sorry, you produce a standard model neutrino. It's going to have some probability, if you're at high temperature, to transition into this state. There'll be interactions with thermal bath. You'll end up with some population of these heavy neutrinos. And for some sets of parameters, you'll have the right amount of dark matter. For some sets, you'll have too much. And some sets, you'll have too little. Basically, it's a power law. So let me just give you 2 points on the power law where this works. Oh, sorry, this is KeV. And this is sine squared theta. Oh, good. I wrote that over here. M divided by KeV. So you can have a KeV sterile neutrino with a sine squared theta of 10 to the minus 7. Or you can have a 10 keV sterile neutrino with a mixing angle of 10 to the minus 9. Limits on this. Lyman alpha limits tell you that the mass of this has to be bigger than about 2 keV. If it's lighter than that, then you destroy too much small-scale structure because it's too hot in the early universe. There are also decays of this into a photon and a neutrino that can be searched for in X-ray searches. And they tend to basically constrain the other region of parameter space so that this is more or less excluded. So if you plug in, if you go up in mass above 2 keV so that this thing is actually acceptable, then the gamma ray constraints, the total rate of gamma rays and the limits you get from the gamma rays basically kill you. So this tells you have to be heavier than 2 keV. These limits tell you that you have to be lighter than 2 keV. That's not exactly right. And as a consequence, it doesn't work. Now, these limits are very, very dependent on sine squared theta. So when I say this is excluded, what I mean is that Dodel-Sin-Woodrow is excluded. But if you have other non-thermal production mechanisms, and people do have other non-thermal production mechanisms, then you can evade these constraints. Okay? But sort of your most garden variety constraints are not there. The last thing that I'll say, and the thing that I'm sort of most actively working on myself on this front, is just to say that what I find especially interesting about this scenario is that this way of presenting it is a very standard model-centric way of talking about it. Okay? I say I start with the standard model operator LH, and then I write down a singlet fermion, and then I start iterating. Okay? But that's not how we think these days, right? We're not standard model-centric anymore. We try to think about dark sectors, and we try to think about connections to them. So if instead you start saying, well, let me imagine a universe where I've got a bunch of generic dark sectors out there, then what you should also be imagining is that all those dark sectors naturally also have LH operators of their own, just in the same way that they could have F mu nus of their own. Right? So just like they could have a gauge field that could mix to us, they could just as easily have the equivalent of an LH operator of some gauge field that gets Higgsed. Right? And that LH operator is naturally going to talk to N2. Okay? So you've got a certain set of these right-handed fields around, and those right-handed fields should go around marrying off against all the LH operators of the universe. And what's interesting then is the following. And this is all I'll say about this because it's just it's in progress. So what people have thought about in the past is this idea that you could imagine that people have definitely thought about something like this in the past, where you say, suppose I've got some operator like YLHN, and then I've got some other operator like phi chi n, and then you add in a mass term, mn n squared, then you integrate out mn effectively, and you now have an operator YLH phi chi over mn. Then you put in a vev for phi, you put in a vev for h, and you now end up with something like md nu chi. But the interesting thing about this is that chi could have been charged under its own gauge group. And if chi is charged under its own gauge group, you now have a mass mixing between the neutrino and somebody who had its own interactions. So you're kind of mixing into this interaction. The problem with this picture, and this is where most of the work has been done up to this point, is that you have a constraint, which is that if you have this mass mixing, then either this mass mixing better be very small if it's Dirac, or you need to add in some mass term. And then when you diagonalize this, you have the usual seesaw story, where you end up with a neutrino mass, which is sine squared theta times the mass of this other state. And if you do that, then either this other state has to be very, very light, like a sterile neutrino, or this mixing angle has to be very, very small. But there's a trick that, at least so far as I can see, has not really been exploited in the literature in this context, which is that if instead of this, where nobody has any preserved quantum numbers, if you imagine that this right-handed state has a preserved quantum number, then you end up with the following story. So imagine that you write down YHLN, you write down Y prime, phi chi n, and that's it. And you don't write down this right-handed neutrino mass term. Okay? Well, if you do this, then what's kind of neat now is that you have something which is akin to the effective Z prime. So you end up with a Dirac mass between our neutrino and the right-handed state, and you end up with some other Dirac mass between the chi and the right-handed neutrino, except for that because, again, you have two left-handed states and only one right-handed state, this n is going to marry one linear combination, and the orthogonal linear combination will be massless. The massless linear combination is what we identified with the neutrino. That means that this Dirac mass here can be order MeV or so. And if this is, say, order GeV or so, then you'll end up with a massless neutrino that is actually has a fairly large admixture of an interacting state. And that means that you now have the possibility of having very, very simple models of dark matter, where dark matter annihilates into neutrinos, effectively. Because neutrinos will inherit the interactions of this chi. The light mass eigenstate inherits the interactions of the interacting state. That's just very, very brief, but it's just an aside to kind of say that even at this late stage, it's kind of funny where you sit down and you start playing with these things and you find that things that people have played with for a long time, there are still new things to find. So as I'm stopping, that's sort of actually the thing that I would like to leave you with, which is that the place where I started with is that whenever anybody like me gets up and tells you about what things are interesting, you should be very, very skeptical. That the things that we find interesting are based on our experience and all of our biases and prejudices. And the field, if anything, is moving in a direction where people are broadening their thinking and changing their scope. And as best evidence for that is that 10 years ago, people would invite me to give lectures on exotic forms of dark matter. And now I get invited to lecture on just ordinary dark matter. And that's not because I've changed. It's because what we consider ordinary dark matter has changed. So as you're thinking about the models you want to build, I would just encourage you not to listen to people if people say, well, yeah, I don't like that small parameter. Do you really need to add that extra gauge group? Whatever. Like, you don't know in 5 or 10 years what's going to become, what people become accustomed to and can consider to be natural. And it's really more about what things are interesting and what things we can look for. So that's what I would like to leave you with is that, trust yourselves. There's a lot of interesting stuff out there, and you should go work on it. Thank you.